We present MultiROS, an open-source 3D robotic simulation framework for deep reinforcement learning research. This package interacts with the Gazebo robotic simulator using ROS and provides a modular structure to create ROS-based RL environments. Unlike the others, MultiROS provides support for training with multiple environments in parallel and simultaneously accessing data from each simulation. Therefore, it supports training with vectorized environment for speeding up the training process and parallel simulations for testing and evaluating meta-learning, multitask learning, and transfer learning approaches. Furthermore, since MultiROS uses the popular OpenAI Gym interface, it is compatible with most OpenAI Gym-based reinforcement learning algorithms that use third-party Python frameworks. The reason for development of this package is due to the growing interest in applying deep reinforcement learning techniques to solve complex robotic tasks. One of the significant hurdles in training a robot with reinforcement learning is that the RL algorithms need to dynamically interact with the environment and collect data to make optimal decisions. However, training an RL-based approach directly in a real robot may not be ideal, since the exploration during the training phase may pose a significant danger to the robot platform and its surrounding. Moreover, even with taking every safety precaution, the reinforcement learning-based algorithms still require sampling a large amount of experience to find the optimal policy. Therefore, the motivation is to collect samples in a simulated environment, which can theoretically provide an infinite amount of data to train the RL algorithms and transfer the learned policies to real-world robots. Currently, there are various RL frameworks available for robotic RL research. However, most of them are focused on fast simulations and don't have a clear process of transferring the learned policies to real-world robots. Therefore, using robotic operating system, which is considered the standard for programming robots, together with simulators such as Gazebo for creating RL environments, is in great demand due to the realistic physics approximation and ease of transferring the learned policies to real robots. So, unlike other RL frameworks, ROS-based MultiROS have the ability to easily interchange simulation with real robots, both in the training and the deployment in the real world. Furthermore, MultiROS provides necessary functions for simulating complex RL approaches such as meta-learning and multitask learning, where robots leverage peer experience to acquire new skills more efficiently. MultiROS uses a modular architecture composed of four major components, and they are the Gazebo Simulator, Gazebo Environment Class, Robot Environment Class, and Task Environment Class. The Gazebo environment, which utilizes the OpenAI Gym, is the class that specifies the connection to the Gazebo simulator. It provides the functionality to reset, pause, and resume the simulation. Then the Robot Environment class inherits from the Gazebo environment and provides the necessary functions to read sensors and move the robot. Finally, the Task environment, which inherits from the Robot environment, specifies the structure of the task that the agent needs to learn. Then from the task environment, it outputs observations, reward, and done flag to the agent. The main focus of this package is to introduce ROS-based RL structure for multi-robot and multitask learning research. Its architecture extends the OpenAI ROS and Gym Gazebo packages, which use the OpenAI Gym interface with ROS. Like in OpenAI Gym, the MultiROS structure enables RL algorithm to interact with environments to sample experience to improve its policy. Therefore, by making minor modifications, this toolkit is compatible with most third-party Python frameworks that provide RL algorithms. There are two ways to use MultiROS framework. It provides tools to create custom environments and a set of pre-built goal environments for evaluating deep reinforcement learning algorithms. When using MultiROS, users can launch environments similar to OpenAI Gym using gym.make. Also, users can simultaneously access data from multiple environments at the same time for vectorizing the environments. To create your own environment, the initial stage is building the simulation of the task in the Gazebo simulator. So users can create a URDF file for their own robots or use the files provided by the robot manufacturers to spawn robots in the Gazebo simulator. Then using the URDF files, users can create or add objects and design the scenario of the environment. Here, users can specify the physics parameters and physics engine they require in the Gazebo world file. This Gazebo environment class is common for designing any task and can be directly used without making additional changes. The users only need to inherit from the Gazebo environment class and override the defined mandatory support functions in the other two classes. For robot environment class, users need to initialize the sensors and actuators they need to train the task in the robot environment. Then users can access the data from the simulation to implement any number of helper functions that may require in the task environment class to take action, define observations, calculate the reward, and specify the task stopping conditions. In the task environment class, users need to define the observation space, action space, reward architecture, and terminating conditions using the helper functions defined in the task environment and robot environment. These functions shape the structure of the task, and its implementation solely depends on the developer's intuition. Since we are inheriting from Gym package, users can register different versions of their custom environments using the OpenAI Gym registration method. For the pre-built tasks, MultiROS currently supports 3-task environment for both Fetch Robot and ABB Robot, making 6 pre-built task environments. Each of robot's 3-task environment is practically the same except for the robot and the gripper they use for executing the task. The intuition behind this selection is that it allows the users to test multitask learning algorithms to train robots for multiple tasks. Furthermore, due to the similarity of the pre-built tasks of the robots, the users can test transfer of the knowledge learned in one task environment to perform another using transfer learning approaches. This package current pre-built tasks are multi-call environments created to validate call-oriented continuous control RL algorithms. By default, all the predefined tasks use Open Dynamic Engine as the physics engine and renders the appropriate simulation of the task. The MultiROS package also includes all the necessary simulation files to directly use the MultiROS for testing and validating the RL algorithms. As for the ongoing and future activities of MultiROS, we will introduce additional robots and visual sensors to extend task environments for meta-learning and multi-agent RL research. Another future direction is to enhance MultiROS to support real robots, evaluate the sim-to-real transfer from the framework, and switch between real and simulated robots for sampling experience. Lastly, we want to explore the possibility of adding support for next-generation Ignition Gazebo and other simulators. Please refer to the GitHub page for the complete documentation and more information on the available task environments.